Mm-hmm.
So in the last class, we have seen how to basically calculate the least square regression,
Mm-hmm.
least square regression.
Yeah, he did.
Yes, just a minute. Least least square regression. Okay, and how to plot it? What are the different terminologies to plot it? Now in today's class, we'll be seeing one topic that how to calculate the value of least square regression. How to calculate the value of least square regression. Okay, so the
Mm-hmm.
value that we will be calculating, it would be based on the simple mean and standard deviation. We have seen in the previous class how least square regression is plotted. First, we have to take out the residuals, then need to do the square of it, and then we need to plot that all the thing. I need to calculate that things. So that's very tedious task to calculate the residuals, then square them, then add them, then take the square root divided by n minus 2. Yes or no, Zaid? We have seen how to
Yes.
calculate the coefficient of determination also. R small r square. Yes or no?
Mm-hmm.
That was all the things. So it would be based on the simple mean. Means if we it's mean and standard deviation. What does this mean? That if we want to calculate the least square regression, so we have a specific formula. See what's the formula here? Okay, so you can read this. Here said that regression to the mean means using technology is often the most convenient way to find the equation of least square regression. Means what we have done earlier was very easy by technology, by using softwares, but by doing with our hand, pen and paper, it is a long and very big task, very long task to plot the
Mm-hmm.
regression line to bring its equation. Yes or no? Okay, it is
Yeah.
also possible to calculate the equation of least square regression line using the means and standard deviation. So we can also calculate the equation and the value of the regression line by calculating the means and standard deviation. So he has written regression to the mean. He has given the heading here regression to the mean. Because why? Because we are going to use the simple characteristics of statistic, that is mean. So exploring this method will highlight an important relationship between correlation and slope of least square regression line. Okay, and reveal why we include word regression in the expression least square regression line. Okay, so how to calculate?
Yeah.
We know that generally what we are doing is comparing the two variables. One is the x and one is the y. So the x1 is the, for suppose explanatory variable, and the y1 is the response variable. So what we need to do, we have the data points of x and y. what we need to calculate for x and what we need to calculate for y is x bar, then standard deviation of x, and y bar and standard deviation of y. This is the mean of x, this is the standard deviation of x column, this is the mean of y, and this is the standard deviation of y. So what does the formula
Yeah.
become after this? The formula is generally b equals to r into sy upon sx. Sy sy upon sx. Okay, so that's the
Yeah.
formula. Yeah, this will change depending on which is the exploratory variable and which is the response variable. This will change. Okay, because the least square regression slope. So now see how we have calculated the slope. You know what is b? B is the slope.
Mhm.
Yes or no?
Yeah.
Yeah. So how to calculate the slope is basically we have to take the r. R is the correlation, 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 and sy upon sx is the standard deviation ratio of the standard deviation. Okay. So because the least square
Yeah.
regression line passes through the point x bar comma y bar, the y-intercept is. So you know that the regression line will pass through. This is the slope of the regression line, slope of RL regression line, and he's telling that
Yeah.
as the line passes through, as the line passes through the mean point, the mean point,
Mean points.
mean points, not mean points, you'll say to the points which are the means for suppose passes through the points x bar and y bar. These is the mean and these points are on the regression line. There will be a point y bar somewhat here and x bar somewhat here. So it will be like this. So it passes through x bar comma y bar for suppose like this here. So our y-intercept will be y bar. Our y-intercept will be y bar. So the equation will become, so equation becomes y equals to y cap equals to y hat equals to y bar plus bx. See, yes or no? This is the thing. Is it clear, Zaid?
Yeah, it's very clear.
Yes. Okay. Okay. So this is some important thing that we have to read. The formula for the slope remind us that the distance between exploratory and response variable is important in the regression. We know that if the slope is positive, it will be a positive
Hmm.
correlation. If the slope is negative, it will be a negative correlation. Okay. So least square regression line makes the distances of the data points of the line small only in y direction. If we reverse the roles of the two variables, the value of sy and xx will reverse in the slope formula. So I've told you that if we are looking that on regression line y on x, it will be this formula. And if we are looking for the regression line x on y on x, it will be sy upon sx. And x on y, just it will be reversed. Sx upon sy. Did you got that, Zaid? The
Yeah.
if we change the response variables and this all the things, there will be a change in the formula, resulting in a different d-square regression. That this is not true for correlation, and we know that when we are calculating correlation, when I have told you when we were calculating correlation, so either you calculate correlation of x y or, and I have shown you an example also, or yx, r remains same.
Hmm.
Yes or no?
Yeah.
Yeah, but slope will affect if we are seeing the regression line of y on x or x on y. It is very simple. See here. If I'm for suppose this is x and this is y, the line is coming like this. Okay. But if you look like this, for example, if I change the things, the correlation remains the same as it is positive. But
Hmm.
if I do y and if I do x, The it was going like this, correct? Y and X.
Yes.
I have rotated. So it will be for suppose I cannot visualize it here, but I'll show you an example further. What will happen in Python, I think. Okay.
Mm-hmm.
So that's the thing. So just remember that if we change Y on X or X on Y, the things generally change in the regression line. Okay. Okay.
Yeah.
The formula for y-intercepts comes from the fact that the least square regression line always passes through the point. So he's telling that here we have used y bar and x bar. Why we have used here y bar and x bar? Because the regression line will always pass through the points which are the means. Okay. So once we know the slope and that the line goes to the points, we can use algebra to solve the y-intercept. Substituting x bar and y bar into the equation. So produce the equation and he's solving for that. Okay, solving this equation shown in the, okay, that's nothing important. Now on to the next example. Come on, do this example, Zaid. Answer the questions, what he has asked. First, it's very simple. Okay, have you read it?
Yeah, I'm reading. I'm almost done.
Okay, okay, do it.
Okay, I'm done.
Okay, so what's the value? Come on. What is the slope?
Now, the slope is the R? No, wait. The slope is 22.71.
22.71. It's coming to be 2.75. See, you have done
Yeah,
the,
2.75. Yeah,
correct.
around that, my
And
bad.
the
Yeah.
y-intercepts value of A,
Oh yeah, yeah, it is 2.75.
correct, yes.
Hmm.
And the value of A, the y-intercept,
The value of A is 103.34.
correct, good, good. Okay, so now he has, here see what he has done, calculating the slope and all the things by these formula. He has taken the equation. He has done the regression line equation, given the equation of regression line has to be y hat equals to A plus bx. Okay,
Yeah.
so now he is explaining that this equation says that along the regression line, a change of one standard deviation in x corresponding a change of r standard deviation in y. When the variables are perfectly correlated, r equals to +1 or -1, we know that. The change in the predicted response variable, that's y hat, is the same as the change in the x. For example, if r equals to 1, as x is two standard deviations above x bar, then the corresponding value of y hat will be two standard deviations above y bar. That's all the simple things. Okay, he's explaining here that if some value mean height is this, then the mean height of y hat will also be this and standard deviation. Okay, okay. See here,
Mm-hmm.
he's explaining. Means what he's trying to explain is that when a student's foot length, what I'll do, I'll copy this. Okay, what he's trying to explain that When a student foot length is one standard deviation above the mean foot length of x bar means what? Or suppose this is our regression line, and when a student's foot length is one standard deviation above the x bar. For example, here is for suppose x bar, and our student length of the foot is one standard deviation away. For suppose our x bar was 5 and our standard deviation was 1. So what will be the foot length of the student? It will be either 4 or it will be either 6. Yes or no? Because it is one standard deviation to the left and one standard deviation to the right. The predicted height
Yeah.
y hat. So we are doing for this x bar, for this x bar, we are predicting the y hat. We are predicting the y hat. Okay, so what will be the things here for these two increments in the standard deviation? So what is trying to explain that the predicted height y hat is above the mean height y bar. So it will, for if suppose it is above standard deviation is to the right, so the y hat will be up of y bar. Yes or no?
Yeah.
The y hat will be above y hat will be above y bar, and if it is the standard deviation is 1 to the left, then the y hat will be below y bar. You got that, Zaid? It's very easy.
Yeah.
Yes, but mean height
Uh,
is above the mean height y bar, but not an entire standard deviation above the mean. It will be above y hat y bar, but this will be not a whole standard deviation, not an whole, not a whole standard deviation. Means how this point is coming a whole standard deviation. This point is coming an whole standard deviation with standard deviation 1. Okay, but this predicted value will not a whole, not be a whole SD standard deviation above the mean. How far above the mean is the value of y bar? So if it is not one standard deviation, then how far is this? So for the length from the graph, we can see that b equals to slope. So what we need to calculate? Change in y upon change in x. For earlier, we know that b equals to this in this. Now setting these two equations equal to each other, we have. So they have set it the equation. They have compared the things. Likewise, they have compared b equals to r into sy upon sx, and when we need to calculate the for this slope for this graph here, what he has taken that is equals to change in x upon change in y. We need to calculate a change in y. Now we are equating these two. So what we'll get? So this will get cancelled. So r sy will be equal to this. So thus y hat must be r into sy. See. So thus y hat. This is y hat. The predicted must be r into sy above the mean. Means this height will be r into sy. That's the thing
yeah.
we have seen here. Okay. So in other words, for an increase of one standard deviation in the value of the exploratory variable x, the least square regression line predicts an increase of only r standard deviation in the response variable. Did you got that? This is the
Yeah.
thing. The least square regression line predicts the increase only in r standard deviation times the of the response variable. Okay. So this is called
Yeah.
regression to the mean. This all the things is called regression to the mean. We are calculating the regression based on the mean x bar and y bar. Yes or no, Zaid? What we have seen in this
Yeah.
whole topic? Yeah. So this is the thing. That's very easy. Now we'll move on to some example. See, correlation and regression wisdom. What is trying to explain that correlation and regression are powerful tools for describing the relationship between two variables. When you use these
Mhm.
tools, you should be aware of their limitations. And I have told you, correlation we know where it is limited, where we should take cautions in correlation. We cannot predict anything by correlation. Just we can define the association of the two variables, that the exploratory and the response variable. That's the limitation. Now we'll see correlation and regression wisdoms and its limitations. So there is a thing we'll read here. You can calculate the correlation and the least square line for any relationship between two quantitative variables. Yes, but the results are useful only if the scatter plot shows a linear pattern. So these correlation and regression line, least square regression is very useful, very much useful if there is a linear relationship between x and y. You know what is linear? Here in the two graphs, you can see here in the two graphs. The second one is not linear, it is a curve. Yes or no?
Yeah.
Yeah, so that is the thing. So, but the results are useful only if the scatter plots are linear pattern. Also plots your data first. The following four scatter plots shows very different relationships with which one do you think shows the greatest correlation? So which will have the greatest correlation? See,
Mhm.
now
Which
he
one has
has,
the greatest correlation is the first one.
yes, correct. But now when we are calculating, when he's calculating the correlation, so all
Oh,
four have
but yeah, it's all four has the same
same correlation.
correlation,
We
more or
cannot
less.
generally, it's not easy to just look at the figure. Yeah, it's not your mistake. So all the four have the same correlation, r equals to 0.816. Furthermore, the least square regression line for each relationship means the least square relation line for all the four is the same. That's the y hat equals to
Yeah.
3 plus 0.5x. These four datasets developed by statistician Frank and Scom illustrate the importance of graphing data before doing calculation. So what he is telling, before doing any calculation and calculating the regression line of the things, what we need to do is that plot the data first. Okay, and look onto it. See, in the each of the four graphs, we can see that the correlation and the regression line is same, but the prediction is different. Yes or no? If we predict some value for this graph, it will be different for this, it will be different for this, and it will be very different for this. Yes or no, right?
Hmm.
Yes, that's the thing he's trying to explain, that there is a limitation. As for different graphs, the y predicted value will change with having a different pattern. All the four have a different pattern, but also the correlation is same and the regression line equation is also the same. Okay, so what we this is the limitation now, that correlation r is not, you already know that correlation r is not resistant. Not resistant means if there are outliers in the data, the correlation changes. Yes or no? Resistance means I've told
Hmm.
you one unusual point in the scatter plot can greatly change the value of r. That is the least square regression line. The following activity will help you answer this question. Now we are going about the outlier removal from the data, which is the outlier. Because see here in this graph, this point is generally the outlier, which is making the correlation and the least square regression line same. This point is the outlier, same here. Okay, there must be some point here also, which must be an outlier. So we'll see it. Okay, so see. What he's telling that in this activity you will use the correlation regression applet to explore some properties of the least square regression line. So here he is explaining some of the properties of the least square regression line. So what will be in that click on the graphing area of the 10 points, it will plus to x bar and y bar. If there is something important, I'll explain. Wait, if you were to add 2 points on the, okay,
Hello?
he's just, yes, he's just explaining you when we add data points into the data, what happens to the value of r square. You can just read it. It's simple. Okay. So
If you add a point that's an outlier, then it will change the R squared
cor-
correlation.
correct. See here, he has given this thing. It's very important. See how majorly. the outlier affects the points. The thing is not clear here. What I'll do, my main thing was the graph. That's why I got clear. Okay, yes, okay. So you can see this in these points, the correlation R is 0.41. Just in this data, what he has done, he has added 1 point here. So what does the correlation changes to, Zaid? It changes to 0.94. Yes or no?
because it's more closely
Yes,
related.
yes, more correlated because 1 point that is very far away, which is an outlier, which is very far away from these data points, which have a high value, It what he is doing that due to its high value, as R is resistant of is not resistant. Okay, so he has changing its value. Yes or no, Zaid? You can see it. So this is the
Mm-hmm.
case, what he's trying to explain in the previous
Yeah.
activity also. Okay, so now we'll see here. Now, what we have done, he has added the third point. In the third graph, he has added a point here. Okay, now what this point have done? Reduce the value. Here it has increased,
Value.
and what he has done here, it is decreased. He has decreased the value. If we will add
Mm-hmm.
on to the downside, here he has given this example. See, yes or no?
Mm-hmm.
Yes. Okay, and now the case 4. See what he has done. When we had gone directly onto the parallel side of the points, what he has done not affected the value so much. Just he has reduced. Just he has reduced. Here we have gone on to negative, onto the negative correlation directly. Now he has reduced the correlation from 0.41 to 0.11. These were the four things where we have to look on. Okay, now comes on to the next thing. That's what in see here. We'll read it first, so we'll get an idea. Just a minute, Zaid. I'll drink some water.
Okay.
Thanks for waiting, Zaid. Okay, so high
No
level,
problem.
outlier, and influential point. We need to read this. Compared to case 1, the slope of the least square regression line is the same. Okay, but the y-intercept, this y-intercept here in this, it has changed. Looking at to the case 1 for the case 4. Okay, the regression line in all the cases was the same, 3.04. Here it has changed in the case 3 when it was negative correlation. See, the slope has become negative, yes or no? And here the slope
Yeah.
was positive, 0.65. Just see the variation in all the four cases. When we are adding to the higher point, what he is doing, see, when we have added to a higher point onto the line here, the y-intercept and the slope has not changed. Yes or no? Seeing the both the
Mm-hmm.
lines, you can also tell me that the line has not changed. Therefore, the regression lines equation has not changed. What has changed is thus the correlation value. So that's the thing. Now, in the case 4, what we have done is that due to the addition of 1 point upside, so it has changed the y-intercept value as the line will move upwards. As the line will move upwards, okay? So the y-intercept is a little larger. As the line appears to have shifted up slightly, yes or no? The values of r
Mm-hmm.
and r square are much smaller than before. And as we have added this point here, so the value of r here is the smallest in the positive sense. Most smallest is there in the negative, but in the positive it is the smallest. Okay, so are much smaller because the new point have such a large residual. The standard deviation of the residual is much larger. In cases 2 and 3, the unusual points have a much bigger x value than the other points. Points whose x value are much smaller or much larger than the other points is these. Then the other points in the scatter plot have high leverage. Note this, okay?
Yeah.
if x
Mm-hmm.
have in if x has a very higher value or much lower value, smaller value in a scatter plot, then it is called as high leverage. In case 4, the unusual point had a very large residual here. Here in this case 4, large residual means if we draw a line onto here, the distance is very large into y predicted and y usual. So y predicted and y actual. So it will be very high residual. Points with large residual are called as outlier. Mark it down. Point with large residuals are called as outlier. All three of these unusual points are considered as influential points. Means what? We'll do a thing.
Huh?
Yeah. What we'll do?
Oh, you
Influential.
said something?
No, no. Influential points.
No? Okay.
Influential points. What are influential points? It is two things. One is the high leverage, and the other thing is the outlier. So first we'll write about the outlier. Outlier. Oh no, outlier. I have written out. Very, very high residual. I have told you. Very high residual. I'll give you an other explanation also. High residual, or we can say a point which is very much, a point which is very much, a point which is very much far away. This will not be a residual outlier, but this will be an outlier. This one, because it is very much far away from the whole data set.
Mm-hmm.
Yes, you can see it that it is very much far away from the whole data set. So it's generally, and what is high leverage? Points with high leverage in the regression have much larger or much smaller x values than the other points in the data. So what he has explained, for in case 2 and 3, the unusual point had a much bigger value than the
So
other
an
points. See,
outlier that seems unusual. Okay.
correct, correct. On the line. This in case 3 also, this was not having a high residual, but it was having very less value. Yes or no? Same thing as here.
Yeah.
Here it is not having a high residual, it is on the line, but it is having a very large value. So what it is doing, it is changing the correlation coefficient, decreasing and increasing the correlation. Yes or no? So
Yeah.
that's the thing. It is called as high leverage outlier, and these two things, high leverage and outlier, are called as influential points. Okay? An influential point in the
Mm-hmm.
regression is any point that, if moved, subsequently changes the slope, y-intercept, correlation, coefficient of determination, or standard deviation of the result. If by any point, by any point, write it here. If by any point the correlation or the y-intercept or the x or the slope, you can say slope, or the standard deviation is changing, then that point is known as then that point is known as influential point. Influential point. And there are two types of influential point. One is the outlier, and one is the high leverage. Is the difference between these 2 points clear? High leverage and outlier. Yeah. So outlier and high leverage points are often influential in the regression calculations. So the best way to investigate the influence of such point is to do regression calculation with and without them. So if you want to calculate that some point is a influential point or not, so what we can do, just eliminate that data point and calculate the regression line, and then put again that point and calculate the regression line equation. So you can see the difference. If the any one of the thing is changing, then there will be a subsequently more difference in the regression line. Is it clear, Zaid? All the things? Yeah,
Yeah, I never got it.
yeah, you got it. I know. Okay, so here is some example. Okay, so we'll look onto this one. Come on, read this example, Zaid. See what, first of all, read this example. Come on, read this. Does the age at which a child begins to talk predict a later score on a test of mental ability? A study of the development of the young children recorded the age in months at which each of the 21 children spoke their first word and their GSL adapt score. The result of an aptitude test taken much later. The scatter plot of the data appears along with a residual plot. What he has given? He has given a scatter plot and as well as a residual plot also in this thing. So what we have in the residual plot. So scatter plots of the Gesell adaptive score reverses the age first word of 21 children along with least regression. Okay. So what we are seeing that the point of child 18 has high leverage because see the point of child 18 here, this one. Yes or no? So it is a high leverage.
Hmm?
Correct? Whether it be an influential point or an outlier, I think it is its residual is not very much high, but it is
I
changing the
don't think it's too high or too low. I think it's just an outlier.
it's not an outlier, it will be an influential point. It's an outlier or a high leverage. This one.
Really? I thought I'd say it's either too small or too high. Oh wait,
Correct.
it's not quite outlier if it's
Correct.
too
It will not
high
be an
or too
outlier,
small.
but it will be an this high leverage point. Yes or no?
Yeah.
Yes. So this will be an outlier because this it has some specific residual. Yes or no? Child 19. Okay, so child 18 has high leverage because it is x value is much larger than the x values of the other points. The point for child 19 is an outlier because it falls outside the pattern of other points and has very large residual. Okay, that's good. So you can see the regression lines, difference in the regression lines when we are putting these points and when we are removing these points and then plotting it. Okay, so you can see the removing point of child 18. Now he has explained this graph. Now how to remove that point 18 and plot that without, see this blue line, upwards line is without child 18. This downwards line is without child 19. And this, the green one was with both the points. Okay. So likewise, your child 19, the strength, and he has compared the different strengths and all. So think about it. What should we do with the unusual points? What you should do? We will generally remove that points from our data point, telling us outline. Okay. So this is an example. Come on, read it. We'll do this and we'll stop. Come on, read this thing.
Mm-hmm. I'm not sure. I don't see the graph.
You don't see?
No.
Okay. Oh, graph. Okay, sorry.
Alright. But I'll let the graph will decrease or increase. I think it will increase. Yeah, it will increase a little bit more.
Correct. Which one? There are 2 points here.
The Los Angeles Chargers.
Correct. Los Angeles Dodgers has won the equation, the least square line. Explain your reasoning. So, what the scatter plot shows the payroll in $1 million and the number of wins of Major League Baseball teams in 2015, along with the least square regression line. The points highlighted in red presents the Los Angeles Dodgers far right and Cleveland Indians upper left. Okay, upper to the left. I think this is for Indians. Yes or no? And this is
Mm-hmm.
for I think Los Angeles Dodgers. Yes.
Yeah.
Okay, so this point will be high influence, high leverage, and this point will be as outlier. Yes or no? See, because the point Los Angeles Dodgers is on the right and below the least. Okay, so this is Los Angeles Dodgers. So this will be least square regression line. It is making the slope of the line closer to zero, the y-intercept greater. If the Dodgers point was removed, the line would be steeper. So what we can conclude that this will be a high leverage point. This one, this red one that I have marked here, this one. And here its residual is more, it is far away from the line. So what it will do, generally increase the R also, because the point of the Valiant Indians have a large residual, making the standard deviation of the residual greater and the value of R square smaller. So this will be treated as an outlier. Is it clear, Zed?
Yeah.
Okay, so that you can read this, the next topic. Association does not imply causations. So when we study the relationship between two variables, we often hope to show the changes in the explorative variable causes changes in the response variable. A strong association between two variables is not enough. I have told you further also. He has explaining us again and again that a strong relationship does not show that a change in the value of x will there will be a change, strong change in the value of y. So that's all the thing. What's next? So that's we have finished with 3.2, chapter 3. We have finished with section 3.2. You can revise all the things. There are a bit of sums here. You remember that you have a test on Saturday. Okay.
Yeah.
So on it is on based on the first unit, the two chapters. So you can practice all these sums because we I am going to take a test on unit 2 also after 1 to 2 after our first test. Okay? So you can practice these
Mm-hmm.
sums. The concepts will be more clear. From tomorrow we'll start with transforming to achieve linearity. Is it clear, right?
Yeah.
Okay, so we'll call the reads for today. Okay, you can leave the class. Assalamu alaikum. Okay, if you have any doubt, you can ask in the class. Is it clear?
Yeah.
Assalamu alaikum. Good.
Walaikum salam, Allah Hafiz.